Welcome. Now we're going to be looking at a plate of constant density. So we are finding a centroid of a region in the xy plane. And this region is formed by the x-axis bounding in the first quadrant, the parabola y squared equals 2x, that's a horizontal parabola, and then the line x plus y equals 4, or y equals negative x plus 4. So in order to do this, we need the moment about the x-axis, we need the moment about the y-axis, and the mass. So that means we're going to have to calculate 3 double integrals. If we were doing this within a solid, right, if this was a solid and we were trying to find the centroid, we would have to find 3 different moments, which would be triple integrals, as well as a triple integral mass for volume. So this is significantly shorter than potentially that previous example, or the solid that we found the center of mass for in the video, which was before this. All right, so we need our mass m, our moment about the y-axis for x bar, the x-coordinate of my centroid, and the moment about the x-axis for my y bar, which is the y-coordinate of my centroid. So the first thing I'm going to do, and you can do them in any order, but we need the mass. And the mass, m, is equal to the double integral over the region of delta dA. All right, so what does our region look like? Well, we know we're in the first quadrant. That's nice. We have this guy here. This is the line y equals negative x plus 4. So that line goes about like that. We have a y-intercept and x-intercept of positive 4. And then this horizontal parabola, that looks like this. So the region, if we bound it here, we're looking at this region. Now we have to think about, do we want to set it up with respect to x traveling horizontally first, or with respect to y's, upper and lower bounds? And so I don't want to use dy dx, because if I have to integrate first with respect to dy, you'll notice that my base is always the same, but my top bounding functions differ. So I'd have to split that into 2 integrals. We don't want to deal with that. So we're going to do this in terms of x. All right, so mass equals, what are my bounds in terms of y? We're going from 0, this point of intersection, we can find that right there, is 2, 2. So my y values, we've got y equals 0 to y equals 2. So my second integral, we're going to have an upper and a lower bound horizontally. My upper bound is this line, and that line would be x equals 4 minus y. And my lower bound is this parabola, which would be x equals 1/2 y squared. X equals y squared over 2. Then we have delta. We'll write this as dx dy. So it's always important to be able to determine how to choose those bounds. And I wanted to do, even though it's conventional to put y first, if I had done y first, I would have had to have split this into 2 double integrals. We don't want to deal with that. All right, so now that we have it set up, I'm going to go ahead and take my delta, pull it out in front, and that's going to give me the integral. Oops, I said I was going to do it and I didn't. Delta integral from 0 to 2, and then I have x, and I need to evaluate x. X equals 4 minus y, and x equals y squared over 2. So I've got delta, the integral from 0 to 2, that is 4 minus y squared over 2. We now need to integrate with respect to y. which gives me 4y minus y squared over 2 minus y cubed over 6 from 2 to 0. When I plug in 2, I have 8 minus 2 minus 8 6. That gives me 14 thirds. When I plug in 0, I get 0. So my mass is 14 delta over 3, or 14 thirds delta, however you want to think about that. So that represents my mass. Okay, so now we have two more steps, the moment about the x-axis and the moment about the y-axis. So the moment about the x-axis is going to, again, be that double integral across r of delta, but we have this additional variable as part of our formula, y dA. And of course, the setup is going to be exactly the same. It's just as we work through this, we have that extra y value there. So here is the setup for our moment about the x-axis. Again, my y goes from 0 to 2. My x value goes from my lower bound, the parabola, y squared divided by 2, to the line 4 minus y. X equals 4 minus y. So we've got delta in there, our density, which is a constant, and then y, this extra factor, which we have to use. It's from the formula for the moment about the x-axis. So as I integrate, I have 0 to 2. Actually, I'll go ahead and pull my delta out in front. Delta from 0 to 2. Integrating y with respect to x gives me yx. And I've got x equals 4 minus y, and x equals y squared over 2. So we have a little bit of algebra to simplify. I have y times 4 minus y squared over 2. Integrate with respect to y, so we'll distribute. That's delta from 0 to 2 of 4y minus y squared minus 1/2 y cubed dy. Okay. So I have delta integrating. I've got y squared over 2, so I've got 2y squared minus 1/3 y cubed. Now will become y to the 4th, so minus 1/8 y to the 4th. We need to evaluate from y equals 2 to y equals 0. Plugging in 2, I'm going to get out 10 thirds. Plugging in 0, I get out 0. So my moment about the x-axis is 10 delta over 3. All right, so I'm going to clean this up, go back up to the top of the page. We'll do this one more time. So we have found our mass, and we found our first moment about the x-axis. We need our first moment about the y-axis. The setup, again, is very similar, double integral across r with delta, and we have this times x value in there. So again, that x is part of our formula. So setting this up, what would this look like? And we'd set up the integral the exact same way. We've got y equals 0 to y equals 2. And my x equals y squared over 2. X equals 4 minus y. Delta x dx dy. And I'll go ahead and pull my delta out in front as I know it's a constant. So I've got 0 to 2. I need to integrate x with respect to x, which is x squared over 2, between the bounds of 4 minus y and y squared over 2. So one thing I'll do is I'll pull that 2 out in front. Delta over 2, the integral from 0 to 2. I need to square 4 minus y and subtract from it y squared over 2 squared dy. Here we need to simplify this, so with some foiling magic, we end up with delta over 2 from 0 to 2. Looks like I have on my paper here 16 minus 8y plus y squared minus y to the 4th over 4 dy, which is of course easy for us to integrate. Delta over 2, I've got 16y minus 4y squared plus 1/3 y cubed minus 1/20th y to the 5th. And we evaluate between 0 and 2. If I plug in 0, that will again give me 0. And if I plug 2 into all of these, I get a fraction. Divide that by 2. My moment about the y-axis is going to equal 1/28 over 15 delta. All right, so clean it up, go back up to the top. So here we have our mass and our first two moments about each axis. So in order to find x bar is going to be m sub y over m, or 1/28 over 15 delta divided by 14 over 3 delta. That simplifies to 64 over 35. And y bar equals m sub x over m, or 10/3 delta again over 14/3 delta, which simplifies to 5/7. So my centroid, my center of mass for this region, would be 64/35, 5/7. And so this represents the center of mass, or our centroid, for this thin metal plate. Anyway, I hope that helps you understand it a little bit better. 2 variables, clearly way shorter than 3 variables. Good luck. Email me if you have questions. I'm here to help.